Thank you. So you need to forgive me, I've just come from another speaking engagement where I've talked myself hoarse. So we'll see how we go. So my name's Adam from AWS. Prior to AWS, I used to work at Murdoch University for about 15 years. Did a bunch of projects with Pawsey, so there's a lot of familiar faces in the audience. So I've worked on, I think, XE, Epic, the Nectar node, and a little bit of Fornax. So I know the local crew pretty well. You'd be horrified to know that I think that cloud's got a space in HPC. However, I guess from my perspective, it's not necessarily a religious discussion. I think it's, you can hear me okay? Yeah? I think that it's complementary. So I know from my experience in my previous life that there's a big end of town that needs lots, like a limitless supply of HPC, and then there's a long tail. And trying to deal with those two competing requirements is very challenging. And invariably we end up with supercomputers that get a big chunk of the long tail on there, and it's complex to manage. It's hard to configure the schedulers to balance those requirements. Invariably someone gets unhappy. I remember one particular story from when I was working at Murdoch. Oh, I shouldn't have said Murdoch, but anyway. It was at Murdoch. A particular user had burned through 1 million CPU hours of an allocation and had absolutely nothing to show for it at the end. Now the reason, I won't go into the reason why, fundamentally it was user error. They were fairly naive at using a supercomputer. But it represented a massive challenge. I mean, they've gone through the whole process. They've done an application. They've done a mirror allocation. They've burnt through their time, and they've got to the end. They've got nothing to show what they do. So I got dragged into the director's office one particular day and got presented with this scenario. We couldn't get any more allocation out of the supercomputer center. I mean, why would they? If we just burned through 1 million CPU hours and got nothing to show for it. So what would we do? Turns out the workload was an embarrassingly parallel. It probably should never have been on the supercomputer in the first instance. So we went onto Amazon, got out the credit card, whipped up a whole heap of Spot instances, and ran the analysis through Spot. And that was the happy ending. It was doubly a happy ending because the funding for that project was coming from an American government department. So there was a lot of reputational damage at stake and so on. But I think that when that occurred, there was obviously a keen lesson in there that I learned at the time, and that it was that there's a complementary relationship to be had between the big supercomputing centers and the public cloud, and there's a place for both. And fundamentally, this is the challenge that we face with the machines, where we've got a certain core limit over a given time frame, and we're trying to pack jobs into that machine. And if we're trying to balance between the big end of town and the long tail, that gets very challenging. And in that scenario that I just described, the user doesn't want to be constrained by that box. They just want to run all their stuff now. They want 1 million CPU hours as quickly as they can get them to get them out of the problem that they've created for themselves. And so this is one place, or this is one way that cloud can make a contribution. Sometimes you might think about this as like a burst out capability. And there's different ways to look at this. It may just be a matter of matching jobs to the appropriate architecture and to the appropriate machines. Or potentially just not letting new users onto a supercomputer and burning through 1 million CPU hours. So I mentioned before that we use Spot. I'm not sure if you're all familiar with Spot instances, so I might just explain that shortly. But here's another example of, which is a few years old now. Some of you may have already seen it before. It's the largest example that I've seen of someone taking advantage of Spot instances. So this is 1.1 million vCPUs. So vCPU in Amazon speak is hyper-threaded. So hyper-threading turned on in this instance. Spread across one region in the US. And that's running on the Spot market. So this is 1.1 million cores running in Amazon's spare capacity. Now hopefully I've got a slide here that talks about this. So if we just use, let's just use some artificial numbers. So let's say an Amazon data center's got 100,000 CPUs in it, and there's 60,000 of them used. We've got 40,000 sitting there doing nothing. That's just costing money. That's the basis of the spot market. You can bid on that excess capacity, and you can save up to about 90% of the on-demand price when you use the spot market. Now, for research workloads, this is perfect, and this is exactly what we did in the story that I told at the beginning. We just use the spot market to get a whole bunch of CPU and an embarrassingly parallel workload really quickly and very, very cheaply. So why else would we use HPC on AWS? Well, one of the really good reasons is you can do pretty much whatever you want. So there's FPGAs, GPU instances with terabytes of RAM, obviously just the standard compute instances, and you can just have your own personalized cluster and do whatever it is that you want to do. If you go onto the AWS website, aws.amazon.com/HPC, you'll see that there's case studies and examples of pretty much every sort of industry vertical you could think of running HPC on AWS. So what I really want to get to today is to talk through some of the new stuff that's come out since reInvent of last year. So in reInvent last year, and between then and now, we've had a whole bunch of really cool stuff that's specifically targeted at HPC. One example is in the compute space, one in the storage space, one in the network space, and one in orchestration. So in the compute space, we have the C5N instances. So in case you're not familiar with the sort of code that AWS uses with the instance names, the C means they're dedicated for compute, so dedicated to HPC. The 5 is just the 5th generation, and then N in this instance rather informatively means network optimized. Sorry, my voice is failing. So the C5Ns are interesting. These are relatively new, and the one down the bottom there is even more interesting. The ones that come with EFA, the Elastic Fabric Adapter, which I'll explain in a second. So here we have up to 100 gigabits of networking. These are Intel Skylake CPUs. They're using the Nitro system. I'm not sure how familiar you are with the hypervisor that's used within AWS. Back in the day, it was all Zen. The new instances are all based on a hypervisor that's referred to as Nitro. It's actually based on KVM. A bunch of the KVM code that's not used is ripped out, and a lot of the KVM is actually implemented in silicon. So it's actually a card in the box. That's the reason why AWS is able to do things like bare metal instances. That is, within EC2, you can actually provision bare metal instances, not virtualized instances. So these high bandwidth instances are targeted specifically at CPU use cases. These CPUs also come with AVX 512, so if your code supports that, you should compile for that as well. We have the clicky, so you can click around and fire one of these things up. What I really wanted to show you there is that you'll see there's a little checkbox there to say Elastic Fabric Adapter. The Elastic Fabric Adapter, which I'll explain in a minute, is a little bit different, so you've actually got to click it to enable it. It gives you a little bit of a warning there about placement groups. If you've used AWS before, you're probably familiar with placement groups, but just a little thing that's easy to forget. Basically, stick your nodes in a placement group, they'll be closer together, they'll get better performance. The other thing I wanted to show you on there was down the bottom you'll see that it's got, where is it? Threads per core. That's basically just disabling hyperthreading. And you can actually turn off cores as well if you like. There are a few sort of typically licensing scenarios where people want to turn off cores. So Elastic Fabric Adapter, I've mentioned this a couple of times. So this is a new fabric adapter that's available on AWS, which gives the higher bandwidth and lower latency. So that's available that's the little N indication in the name there. So it's available on some of the compute instances, on some of the GPU instances and on some of the bare metal instances as well. And you can see there some of so up to 100 gigabits per second networking performance. The latency there, less than 15 microseconds. So, I'm sure there's situations out there in IB switches and what have you that can do much better performance than that. But for cloud-based performance, this is certainly more than acceptable for a whole wide range of workloads. Most of you are probably pretty familiar with how this sort of stuff works. libfabric supports EFA out of the box. I think version 1.8 was the first version that added support, which I think is the latest version. You previously had to go onto the AWS website to download it. And it's doing OS bypass. And then under the hood, on the wire, there's a proprietary protocol designed to get the best out of the AWS network. There's support in OpenMPI 3.1.3. I believe there's support in Intel MPI as well. I don't know the version number off the top of my head. And MPISH is coming. So here's a little example of the scaling. It's nothing particularly earth-shattering here. It's pretty obvious. If you get more bandwidth and you get lower latency, you're going to get better scaling. So essentially, the purple line on the bottom is running without EFA, so i.e. it's using a TCP/IP stack on a regular adapter on AWS, and then maxing out around about 400 cores. And then with EFA enabled on one of the newer, larger instances, you can see we probably get about 4 times the scaling. So EFA is new since late last year, so you can get significantly better bandwidth and lower latency using EFA. If you want to get started with EFA, one of the easiest things to do is just go to aws.amazon.com, and if you just search for getting started with EFA, it'll come up with a hit to give you a tutorial and show you how to fire up a box that has EFA. Obviously, you've got to have the correct drivers and so on to do that, and there's a step-by-step guide to do. One of the sort of easy or not so obvious perhaps traps that people run to is with security groups. Security groups are fundamentally designed for TCP/IP, and EFA by definition is doing something a little bit different. So you've got to construct security groups to allow that to happen. Specifically, you've got to allow it on the inbound and the outbound, which is a little bit unusual for AWS. This is a little bit of an outlier. You don't have to do that very often. In fact, this is the only example of where I can think of where you need to do this. Essentially, you need to give the permission so that the EFA can operate. The next one I wanted to talk about from storage is Amazon FSx for Lustre. This kind of blew my mind when this came out. I thought this was, didn't know that this was coming when it came out. I found out at the same time as everybody else. I'm sure there's plenty of Lustre gurus in the audience, and it's just absolutely trivial to fire up a Lustre cluster, a fully managed Lustre cluster on AWS. The performance that you get scales with the size. So obviously the larger your size, the more IOPS and the more throughput and aggregate bandwidth that you get. There's some numbers there in terms of by terabyte as you go up, the aggregate sort of performance that you would expect. One of the really cool things about FSx for Lustre on AWS is that it's the HSM variant. So it's backed by S3. So you can do stuff like you can fire up a Lustre file system, have it backed by S3, and then stage data straight in from S3 into your file system, or stage it back out at the end. So you can fire up a Lustre file system, dump a whole heap of data in there, do whatever you need to do, stage it out to S3, and then delete it afterwards. You can also use it's lazy loaded as well. So if you want to, you can have it as S3 backed, and then it'll be the data will be downloaded as you try and hit it. So that's really cool. The data transfers between FSx for Lustre and S3 are all parallelized, so you can get pretty good performance as well, staging your data in and out of S3. Again, we have the clicky. It's pretty straightforward if you just want to go through the console and fire it up. All I really wanted to show you here is that you've got the options there where you actually tell it as you fire it up in slot 2 there, which bucket are you using to actually act as your stage in, stage out for this particular Lustre file system. And then from there, it's just standard Lustre. Just fire up a machine, as long as it's got the appropriate kernel and drivers. The console will give you the instructions to mount the file system, and away you go. You can do this, the standard kind of command line stuff in the box as well. You can query how files have been striped. You can set the striping configuration when you can create files. All that kind of stuff that you'd probably be familiar with. Another sort of thing I wanted to talk about was orchestration. Obviously with cloud, one of the things that we sort of bang on about all the time is automation and orchestration and not doing things manually, and i.e. not doing the clicky that I just talked about. And if you're keen to sort of have a look at these kind of things I'm just talking about, so C5 nodes, lost to file systems, and just to see how well it works or how well it doesn't work for your particular use case, then I highly suggest you have a look at AWS Parallel Cluster. It's an open source project, it's on GitHub. If you do a search for it, you'll find it. I've probably got a link to it here somewhere. And it essentially will allow you to fire up a cluster. It supports FSX and a bunch of other configurations as well, if you want to. In terms of schedulers, it supports Slurm and SunGridgen and Torque. So if you're curious, I would definitely suggest you give that a go. Try that out. In terms of the architecture, it's pretty obvious. It's a pretty traditional architecture in terms of a cluster. You get a master node and a bunch of worker nodes. Depending on how you configure the parallel cluster, the worker nodes will auto-scale. So as you pump jobs into it, it'll fire up new ones, and as the job queue depletes, it'll turn them off. All that kind of good stuff that you'd expect. Just quickly, there's the links there down the bottom as well on GitHub, and also for the documentation on AWS. So yeah, just find that on GitHub and check it out. It comes as a Python package, the client that you actually use to interact with Parallel Cluster. Just install that via pip. One other one that I just thought I'd show really quickly is a third-party one. This is not an AWS tool per se. This is an Australian startup called Ronin. I don't know if any of you have bumped into it. They've been deploying to a bunch of Australian universities, and I think what they do is pretty cool. One of the challenges that people often face when they start using AWS is you go log in, there's 180 something services, and it can be a bit daunting. And Ronin's got a really nice way of making it accessible for non-cloud nerds. It's also got a really nice way of dealing with the long tail. So you can actually do nice things like give projects budgets and work within those budgets and get notifications and so on. I'll show you a few screenshots really quickly. So essentially what we're seeing here is the UI interface for Ronin to fire up a cluster. So we're selecting what OS we want to use, what scheduler we want to use, how we want to address it, and it supports, I'm pretty sure it supports FSX Cluster as well. So for the long tail, this is really useful. It's got some nice stuff in there like scheduling, so you can just click a button and then all your infrastructure will turn off outside 9 to 5. So that's really cool because on AWS that'll save you a heap. That's like 60% off your cost right there. So that's just one click in Ronin. And I just thought I'd show you this here where essentially what you're seeing here, I don't know how well you guys can see that, but each one of those line items is basically a project, if you like, with a specific budget, and there are users logging in and using that particular project. So lots of universities have been deploying Ronin. There's a URL to Ronin. Systems Manager. Systems Manager itself is not new. One of the things inside System Manager that is new is the Session Manager. I thought I'd just show you that really quickly, just in case you're curious. And what System Manager enables you to do is to SSH into your boxes and perform administration without having them on the internet. It's actually really, really useful because often, particularly with most of the sort of customers that I deal with tend to be government customers, and I've done a little bit of Luster for oil and gas, but mostly government customers. And often there's a huge compliance and security regime, and not being accessible on the internet, not having open ports, and rah. And so System Manager is really, really cool in terms of you can just literally click on one of your box in your clusters and get an SSH session right in the console, and you don't have to configure any outgoing ports for SSH. So I thought I'd just mention that because there's lots of nice sort of operation tools like that within the platform. Some performance considerations, look, I won't dwell on these because most of these things are probably things that you guys are already familiar with. There's a few things that are new in relation to the C5s and C5Ns. In terms of when you're doing benchmarking or test case in the cloud, we always recommend that you do real-world test cases rather than small-scale test cases. So if you remember back to when I showed you FSX for Lustre, many of the services use that kind of pattern. When you start out small, you're going to get a very sort of relatively small amount of bandwidth or I/O or whatever the particular service is doing. You really want to use real-world use cases. Plus, you can just build it up, build your real-world use case, run your test scenario, and then destroy it afterwards. So it's not going to cost you even money. Typically, disable hyperthreading. No doubt you'd be all aware of this. Processor affinity you'd be aware of. Placement groups already mentioned. You really want to place your instances in placement groups so that they're close to each other so you get the best performance. The advice around the clock source is new. I think on the previous hypervisors there was advice to change that. The advice for the C5s is not to do that. And the obvious stuff of use an update OS, and if you're using those Skylake processors with ABE 512, then and your code supports that, then compile for it. One final thing, just before I go, there's a researcher's handbook which has got a really good guide to using the cloud for researchers and for scientists. This is worthwhile having a look at if you're in the space. The URL down the bottom there, it's just amazon.com/RCP. And that's me done. Thank you very much. If you have any questions, there's my email address. By all means, just email me. I'm based in Perth. But I have no problem if people from around the country email, and I'm more than willing to help you out. Thank you.